Dynamic voltage control. The existing method of voltage control in distribution network is based on fixed settings. Tap changers, deadband, HV, MV transformers is set once and it kept same for many years. There will be an occasional change, for example, as a part of a large overall network. But there are some exceptional cases if reference value could be changed. So this would allow a more optimum control of voltage, which is based on the information that is obtained from the measurement at a limited number of location in a distributed network. Method of dynamically adjusting the setting of tap changers on HV bar MV transformer, the so-called segment controller, which collects the information from the load of individual feeders and from the voltage and power flow at selected location on the feeder. So this information is used to estimate the voltage profile along the feeder, which is again based on optimal voltage at a main bus has to be determined. Here, the field experience of 11 kV network in United Kingdom with the 5 feeder voltage and power with 2.5 megawatt wind parks are used as an additional input to the controller. Both the over voltage and under voltage margin are calculated assuming that the limits are 94% and 106%. If one of the margin becomes negative, the reference voltage of tap changes is changed by 1.5% of steps. So again, the measurement during the field trial shows that the method works well at an additional 2 to 3 megawatt that can be added to the wind park without the voltage limit being exceeded. Voltage measurements at a number of essential location along the feeders are used as an input. So the essential location should include the point where maximum voltage or minimum voltage is likely to occur. When one of the voltage is outside its limit, the reference value of the tap changer controller is adjusted in such a way that for any form of dynamic voltage control, it is important to be able to estimate the voltage magnitude throughout the network. However, the number of measurement location available is limited, so the voltage magnitude at the other location should be estimated. A number of algorithms for this distribution state estimations are being discussed in our literature survey of many papers, many reference papers. Uncertainty in the load profile and the power produced by the generators, the latter requires the communication and to limit the demand. So simulation in an 80 node network with 7 generator shows that the accuracy about 1% in voltage magnitude can be achieved. However, it should be noted that the base their conclusion simulations only. So there is no comparison made, and this measurement has been presented it by making a comparison of these values. So this is about a dynamic voltage control. So let us see the compensating generator voltage variations. Moving on, compensating generator voltage variation. A generator producing certain amount of active and reactive power will impact the voltage magnitude for each location along the feeder. The voltage rise due to the injection of active power increases linearly from source up to the generator location and remains constant behind this generator location. Whenever generator is also injects or consumes the reactive power, the voltage may rise or drop. So in that case, a change in the voltage along the feeder is equals to lambda Rp gen plus xq gen divided by u square norm. Lambda is greater than equal to lambda gen, or lambda gen is equals to a ratio of Rp gen plus q gen divided by u norm square. Lambda, where lambda is greater than lambda gen. So by keeping Rp gen plus q x gen equal to 0, the impact of generator on the voltage variation can be minimized. Only a small impact remains due to active and reactive power, which are associated with this transport of power between the main grid and generator. So this Q gen is equals to minus Rx by P gen. So to strongly limit the impact of distributed generation on a voltage variation, each unit should consume a amount of reactive power which should equal to imaginary part of the source impedance at a point of connection where the generator units are connected. With multiple units, each unit can be compensated its own contribution to voltage magnitude variation, and in that way the limit total voltage variation, where the risk of over voltage will no longer be limitation for the amount of distributed generation that can be connected. So the disadvantage of this approach is that the unit should be able to consume the reactive power. So this requires power electronic converter or synchronous machine, especially for weak speeder. For the factor of R by X could reach a large value up to 5 or even higher. So this would require a converter with a rating 5 times or larger as for injecting the active power only. To limit this reactive power requirements of converter, the reactive power consumed by the downstream load could be used as a compensating part of voltage rises. So with the P and Q, the active and reactive power consumption downstream the generator location, so the voltage rise due to the generation plus the demand is equals to delta U is equals to R of bracket P gen minus P plus XQ gen minus Q. So to compensate this reactive power exchange between the generator and feeder should be so Q gen is equals to Q minus R by X P gen minus P. So in this way, generator even contributes to improvement in the voltage profile along the feeder. So this is about the compensating generators voltage variation. So now let us see the distributed generation with voltage control. Distributed generator with a synchronous machine or double fed induction generator or a power electronics interface have a ability to control the amount of reactive power consumed or injected to the grid. So this allows they are used to control the voltage in medium and low voltage network. Most existing wind turbine, even when they have the ability of this reactive power control, are disconnected when the wind speed drop below the cutting speed. As a result of this, reactive power capability is not available during 20 to 40% of time. A decision have to be towards the reactive power support which is available continuously should be made early in the discussion between the network operators and the owners of wind turbine. The possible method for letting the distributed generation actively contribute to the control of this voltage in the distribution network. So the methods were selected for further development by the main French distribution network operators. Using distributed generation to control the voltage at a limited number of locations in the network, a central regulator calculating the required voltage or reactive power references for these individual generators, and a separate active and reactive power control for the generators. So these are some of the methods that were selected for the development of main French distribution. Again, these are selected by the network operators. Okay. Consider the grid impedance effect on a voltage possibility using this power electronics interface with the DC, which is shown in the figure. So a power electronics interface DG unit provides an independent control over injected active and reactive powers. which promotes it as a good candidate to accomplish the local voltage control. However, there are some limitations that should be considered to maintain the stability of the system and the connectivity of DG unit. Four basic limitations are important to pinpoint the short circuit ratio at a connection point, the size of interfacing the converter, DC link voltage amplitude, uses the voltage source converter, and the control system response times. To better understand such limitations, so the equivalent circuit is shown. So ZS represent the short circuit impedance as the it's seen from PCC for simply this impedance is assumed to be okay for better understanding such limitations. So consider for simplicity the impedance here assumed is purely an reactive, that is ZSS. So the power flow through the feeder PF and QF that represents the power mismatch between the distributed generator injected power, so and the consumed load power, that is PL and QL according to the direction indicated so in the figure, so referring this figure. So the following are the mismatches. These are the mismatches. You can see my mouse pointer. These are the following equation for the mismatch. PF is equals to PDG minus PL. QF is equals to QDG minus QL. Also the power mismatch can be read as PF is equals to UPCCE divided by XS sin delta, and QF is equals to UPPCC square divided by XS minus UPCCE divided by XS sin delta. So here the grid voltage angle delta can be eliminated by squaring and adding the above two equations. So using trigonometric identity, the following expression is obtained, that is P square F plus QF minus UPCC square divided by XS whole square. This is equals to UPPCC divided by XS whole square. So this equation represents the equation of circle with the radius and center, which is a different circle, referred to a power circle. So can be obtained for different parameters. The power circles are used here to define the operational limits for DG, which is connected to PCC regarding the short circuit ratio. Two main causes that can be considered in case of first case, that is a change in the remote bus voltage is considered while PCC voltage is regulated. So the power circle represented by injected DG power with a constant local load. So in this case the injected active power of DG should be kept within the following limit. So in order to have this real solution for a reactive power, PL minus E divided by XS is less than PDG is less than PL, that is E by XS. Now let us consider these graphs which are shown here, which gives a reactive power import or export versus active power in per unit. So first is of operational region for distributed generation regarding various voltage amplitude at PCC for SCR is equals to 2 PG. One is operational region for voltage source converter regarding various voltage amplitude at PCC for short circuit ratio, which is 2 PDG. So by increasing this injected active power, so less reactive power will be available to the size limitations of interface of converter. For instance, if the DG is injected 0.8 per unit of active power and voltage at PCC drops to 0.7 per unit. Voltage regulator without fail to boost the voltage up to 1 per unit. So this is basically because the required active power is about zero point 0.8 per unit, which results in the apparent power exceeding 1 per unit. So this may trip the overcurrent production of the converter and electrically disconnect the DG from the grid. However, if voltage regulator is adaptive, in the sense the reference voltage value may change according to the DG operating point. The system may survive through the boosting of voltage to a level lower than 1 per unit. So different solution may result for a higher short circuit impedance. The power circle for short circuit ratio, that is 2 PDG, are shown in the figure. So it is obvious that reactive power is needed for voltage compensation is lower than that case with short circuit ratio, that is 4 PDG. Regarding the same example of this graph, so DG injected 0.8 per unit active power at the voltage PCC drops to 0.7 per unit, which is about 0.4 per unit reactive power. Instead, to boost the voltage level to 1 per unit, and this is possible operation, so opposed to the case so where the operation limitations mentioned above are due to the network parameter, and they give theoretical boundaries for local voltage regulation. PCC, for an ideal generation plant, there are also an operational limitations due to this physical configuration of DG itself and its control algorithm. So regarding VSC interface, so there are basically two limitations that affects the transfer of reactive power through the feeder. First is the current amplitude limited in order to protect the semiconductor for voltage source converter through current over current production. So this limitations is highly impact to the compensation of PCC voltage by using injected reactive power of DG. Since the maximum available active power from DG is usually injected to the grid, a small amount of reactive power available without violating this current limit. So this eventually means that certain voltage quality phenomena at PCC may be compensated because of lack of reactive power. The second limitation is that converter DC link voltage amplitude. So usually it is in the ratio of 1.12. So there is a schematic simplified VSC DG, voltage source converter distributed generation control system, is shown here. So this also limits the reactive power transfer, which is basically controlled through changing the converter voltage amplitude. First limitations is discussed, while the second limitations is more elaborated. Since the control of active and reactive power can be performed independently, the active and reactive current can also be treated as independently. A simple schematic diagram of overall voltage source converter is shown in the figure. Here the control reference limitations block the over voltage. So it is assumed that initially the converter is injecting a current vector A. This means only active power is injected. The quarter cycle in the figure represents the maximum allowed converter current. So if the voltage at PCC is reduced, so within the voltage regulation using DG, an injection of reactive power is needed. Assuming that the current command for converter moves from B implies that increase in the amplitude above allowed value. Since such operation is not possible, the current limitation protection may change the command to the current vector C. So this vector will provide less reactive current that is required for voltage regulation, hence the voltage is not exploited fully. Other current limitations algorithms are also possible if reduced in active current of DG lies in within acceptable limit. So Consider a graph which shows reference of current limitation where zeta represents the possible active power for curtailment. Assuming that energy produced of this DG unit is allowed to reduce by a value of zeta, two current limitation algorithms are referred, that is L1 and L2. So in the figure with L1, the reactive current reference is limited in such a way that to reduce injected current amplitude and to maintain the current vector angle. Using L2, both active and reactive current are reduced in such a way that to inject as much as reactive current is possible to the grid. The limitations over maximum allowed reduction of active current zeta will affect. So in this case, the amount of injected current, so referring to the our above figure, so the current vector originally lie at A. So in case of change in the voltage amplitude, it moves to B. Using L1, it will be limited to D, while using L2, it is limited to E. Generally, and any limited current vector lies between C and D is possible. So this is about the current vector or the voltage control of this distributed generation. So in coordination with the distribution generation, the voltage control, how to control the voltage. So let us move on to one more topic, that is coordinated voltage control. So here the over voltage may be curtailed by reducing the power production. So it has been assumed that generator neither produce or nor consumes the reactive power. When many units are connected which are close to proximity, it has been shown that the curtailment of individual generator can be expressed as a ratio of maximum production. So when different types of generator units are included, so there might be an condition that some units cannot curtail their share, and hence other would have to increase their share of curtailment. Moreover, some units may have the capability to produce and consume the reactive power, which in turn will impact our voltage profile. If two identical units are connected close to each other, both are equipped with voltage control that takes same terminal as voltage as a input, so they would provide exactly a same power to compensate the terminal voltage decrease. Okay. So voltage control coordination is essential in transmission and distribution grid in order to maintain the voltage within acceptable limit, and at the same time to prevent counteracting operation of individual active devices and maintain the stability. So generally having a parallel device with the same assigned function is also beneficial for operational point of view. Regarding the power sharing and reliability, while maintaining the n-1 criteria, so the Drup scheme is a classy way of coordinating different active devices without need of any communication signal between them. So it is derived from the power flow equations, assuming an inductive feeder with the reactance X and power angle where the power flow from A to B. So power A, active power is given by UA UB divided by X sin delta. Reactive power QA is given by UA square minus UA UB X. For further assuming that UA UB are small, it is predominant that the power angle delta is more sensitive to the changes in the active power flow, while voltage amplitude is more sensitive to the change in the reactive power. Hence, by adjusting P and Q independently, the frequency and amplitude of grid voltage are determined. So this is the basic for well-known frequency and for this voltage Drup control through active and reactive power respectively, which is expressed as that is F minus F naught is equals to minus Kp P minus P naught, U minus U naught is equals to Kq Q minus Q naught, where F naught, U naught, P naught and Q naught are normal operating points. So So they are initially assumed to be zero. So the constant Kp, Kq determine the amount of active and reactive power that is to be injected uh, are consumed at a connection point. They actually represent a virtual impedance between active unit and the grid, so which is implying that the increase will proximity means by different amount of correlative signals will be injected. So moreover, each unit does not aim at a full compensation of voltage. So hence if all the units have same droop curve and operate at a same time, the voltage amplitude probability would not exceed a limit. So this uh, we wind up this coordinated voltage control. So let us move on to increasing the minimum load. We'll see the effect of increasing the minimum load. So increasing the electricity consumption might be seems a strange method to allow more renewable energy to be connected. There are, however, cases where this makes a sense. The energy from some type of distributed generation will go unused, and where they are um, not produced. For example, wind, sun, wave, and flow of river are obvious example. So, in other cases, it is not possible or a practical to turn off the types of electricity consumptions. So that can be shifted in time without having a huge impact on the process. So the charging of electrical car is often mentioned in many discussion, but this is not obviously holds for all type of charging, also heating and cooling process. The use of electricity can be somewhat shifted in time, so the dedicated battery storage has been proposed uh, as a way of preventing the over voltage. So there are a number of methods for linking the excess of production to increase the load. So direct communication between the production and consumption is possible. This has been proposed as a way of using the solar power charged cars. The charged would normally operate below its capacity, but when the voltage at the generator terminal get too high, the charging process is accelerated, so to reduce the voltage. When this is not still enough, the production is reduced. Another option is to use voltage directly to control the load in similar way as the power frequency control with conventional generators. A high voltage point will surplus of power which is compensated by increase in the consumption. Also, the under voltage could be mitigated in this way with electric car. So charging would go faster when voltage would be high, and slower when the voltage would be low. Some control algorithm could be implemented so in the charger, and heating and cooling load. As a result, the indoor temperature would depends on the voltage of grid. So the third option is to use the market based scheme where different loads and generators put into a bids for a consumption and production. A sulfurous of production would result in a low price, possibly even for a negative price. So this is the disadvantage of such scheme is, however, extensive need for a communication. And also you can see that local battery storage in combination with solar power has been studied in Japan. One of the experiment, the total 4 megawatt photovoltaic generation is combined with 1.5 megawatt battery system for 5 year test. The installation is connected to 33 kV network. So one of the aim of the study is to develop the control algorithm for optimal use of battery storage. Conflicting requirements here fulfilled, including the participation in the electricity market and prevention of overload and over voltage. So optimal scheduling of battery storage depends on the load and also voltage pattern on feeders. In combination of solar power and battery storage is described, that is the following control algorithm is used. What you are seeing in slide is of control algorithm what they have employed, that is voltage between 119 volt, that is of discharge battery, voltage between 119 and 121 volts is a dead band, voltage between 121 and 124 is a charged battery, and the voltage above 124 volt is a disconnected generator. So STATCOM is combined with energy storage. So in their paper they have presented that a fast voltage fluctuations and maintain more constant production over long time scales. A local energy storage can be used to keep this voltage profile within its limit. So the calculations refers to this study shown that a few percent change in the voltage profile along this medium voltage feeder, so would require between a few hundred to few megawatts during 2. This I will conclude the session at the end of the session. So thank you, students.